Hi, I'm Martin. I'm one of the guys at Kistler dealing with so-called charge amplifiers. Whenever you want to measure with piezoelectric sensors, you need such a device to convert the sensor's charge output into a proportional voltage signal or into digitized values for further processing. So far so good, but there are so many different options, so how do you choose the right device for your task? Of course, there are some obvious criteria like number of channels or if the device also needs to support IEP sensors. But then it gets more difficult. The basic rule is the better you already know the signal to be measured, the easier the choice and usually also the cheaper the solution. First questions are how big are the signals you want to measure and have you already selected your sensor? If so, you should have the sensitivity value, which tells you how many picocoulombs the sensor delivers per physical quantity, like Newton, for example. The nominal sensitivity value you find in the datasheet. By multiplying the sensitivity value with the expected signal size, you get the amount of picocoulomb you want to measure with your charge amplifier. Measuring very small signals mean that your amplifier needs to have a very low noise floor so that the quality of your signal is still high. On the other end, if you want to measure very big signals, you need a charge amplifier that can cope with big charge signals. High-end amplifiers like the 5018, for example, can handle both very small but also very large charge signals. The next important criterion is the frequency range. Here, two factors are essential, the lower and the upper end of the frequency range. Other than one might expect, the lower end is technically challenging on a charge amplifier. Piezoelectric sensors deliver relatively small charges as a signal. So basically every lost electron means lost signal. The slower a signal is, the more difficult it is not to lose any electrons by low insulation. So if you want to measure very slow signals, let's say far below 0.1 Hz, we call it quasi-static. Pure dynamic amplifiers for frequencies above 0.1 Hz can be built in a more efficient way, since phenomena like drift by low insulation are filtered away by the high-pass characteristic of such pure dynamic amplifiers. The LabAmp 5165A, a very versatile dual-mode charge amplifier and data acquisition device, is a very good example of such a pure dynamic amplifier. The faster your signals are, or the higher the frequency content of your signal is, the wider the frequency range of your amplifier must be, of course. Some amplifiers go up to 2 or 20 kHz, but others go even higher, up to 45 kHz, for example, like this quasi-static LabAmp 5167A. High-end laboratory amplifiers have their -3 dB limit at 200 kHz, like this 5080, for example. So summarized, the more you know about your signal in terms of signal amplitude and frequency, the more targeted your amplifier selection can be. The less you know about your signal, the more it might be worthwhile to think about a high-end charge amplifier, since this device covers basically every piezoelectric signal. Check out our signal conditioning product finder on kistler.com or ask one of our experienced sales colleagues in your region. They for sure know how to help you.